Today's lecture is going to be all about meso compounds. This was a subject that really made my three-dimensionally challenged brain hurt. So I'm going to have a bunch of model kits. I'm going to draw a bunch of stuff on the board. Please, if you have any questions, ask me. It's really hard to communicate this kind of information without actually being in a class. But first of all, we got to start with a definition, right? What is a meso compound? Miso soup, not miso soup. That's M-I-S-O. Meso is M-E-S-O, and they are special compounds that have asymmetric carbons, which we've been talking about, right? Carbons bonded to 4 different things, but are not chiral. These are really tough to pick out. I'm going to show you a couple of tricks for actually figuring out that something is a meso compound, so stay tuned. Okay, so what I've done is I've built a meso compound, and we're just going to kind of manipulate it. We're going to do our normal trick for testing for chirality and everything else, but I'll do like an unnecessary zoom here. And so you can see this meso compound, right? And I could twist it around, do any of those other things. But what you'll notice is that these 2 carbons right here that I have my fingers on, they are in fact bonded to 4 different things. So they're asymmetric carbons, right? That's our definition. And 99% of the time, you have an asymmetric carbon, and you're going to have a non-superimposable mirror image, right? That's the key to chirality. By the way, keep in mind that idea of non-superimposable mirror image. It's not just that these things have a mirror image, it's that it's non-superimposable, right? And so that's one thing I want to see you guys use more when you do your answer your homework questions and things like that about chirality. So let's show that, in fact, when I make a reflection of this in a mirror, let's show that it is, in fact, an achiral compound, right? Achiral means it has a superimposable mirror image. So here is the compound, right? And I've already made its mirror image right here. Right? Let's see if I can get it on the camera. Right? So you can see very clearly, if I can get my hands out of the way, that these guys are in fact mirror images of one another. And now the ultimate test, after I make the mirror image, is to try to superimpose them. And when I do that, you notice that everything matches up perfectly. And so what the heck is going on here? Turns out that this, right, this compound, they're both the same, would not rotate plane polarized light, right? It is achiral. So, how are we going to recognize it? Well, the first thing that we're going to do is we're going to take this compound and we're going to find a mirror plane. It turns out anything that is meso has a mirror plane. And as I've drawn this thing, as I've built this thing, it's probably fairly straightforward for you guys to notice that there is not a mirror plane here, you silly, right? That side doesn't reflect into that side. But if I turn it like this, you'll notice that if I cut directly on this center point, everything reflects into each other. And really, that's the key to looking at something and recognizing it as a meso compound, right? There are other ways, and they all depend on being able to assign RNS designations. So let's kind of go through a little bit of that right now, and we'll see how you guys are at this. So here is our meso compound that I've drawn on the board here. And you can see that the reds that I have shown on there are actually just fluorines. It could be anything, but I just chose fluorine to make sure that you could see it here. And so obviously what I'm saying is that there is a mirror plane directly through this bond that takes one side and reflects it through to the other, right? And that's the key to recognizing something as a meso compound. Let's see what's going on with the RNS designations. So I purposely drew it like this so it's easier for me to talk about RNS because that hydrogen is projected behind the plane in the way that I've drawn it here. And obviously it's not going to be this easy when you get to like homework questions and stuff like that. You may have to do some manipulation and use some of those tricks we've talked about in other videos. But if we go through and prioritize our atoms, we'll just work with this asymmetric carbon to start off with. We've got 1, we've got 4, and remember these all have to do with the molecular weight and the first point of difference. If you don't remember that, go back to the RNS designation video. we look at these two carbons, and they're both carbons, so what we're going to do at that point is to do our Kohn-Ingold pre-log rules and do something like that, and you list all the atoms that are bonded to that particular carbon in descending order. Well, that one's pretty easy. Those are all H's. That guy is a carbon bonded to a fluorine, carbon, hydrogen in that order. And so you might recognize, based on that, that carbon wins against the war with this little methyl group over here. So hopefully you can see that. I make sure that that group is projected back, the lowest priority. I go 1, 2, 3, right? And so I've got an R. So let's write that on there. We'll write an R in blue. So this is an R carbon. Now we'll do the same with the other asymmetric carbon in this thing. And I apologize for the shade. Hopefully you guys can still see stuff. Not really any better, I guess. But anyway, so we've got an asymmetric carbon. That's still first priority. That's fourth priority. 1, 4, and just like before, that carbon is going to lose to that carbon in terms of priority, and we've got 1, 2, 3, right? And so that's a counterclockwise kind of thing. So that is an S carbon. So notice what you have here on this flat structure. You have, yes, a mirror plane if you can see it, right? Or what you can do is to recognize that if you kind of have one side of a molecule that is bonded to the exact same set of things as the other side of the molecule, and you have kind of this interior mirror plane, you'll notice that when you go from one side to the other, it switches from an R to an S, right? Which makes sense for a mirror. You know, if I hold my hand in a mirror, then I see my other hand, essentially, right? So this kind of thing, you could imagine if it wasn't just, 2 asymmetric carbons, what if it was 20? Well, in those 20 asymmetric carbons, whatever the RS, 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 RS is of those 10 on the left side have to be the exact opposite from the right side, right? And so that's one of the really great benefits of R and S is that when you have big molecules where you can't necessarily see stereochemical relationships without a model kit, you can kind of get enough practice that you can recognize certain patterns here. So that's going to be, or I should say, meso compounds are not something that's very common in like even biochemistry and things like that. Usually if you have an asymmetric carbon, then you're going to be chiral, right? This is a really, really special case. And you can kind of see this in that when I take this system right here that we recognize as an R and an S, what happens if I, let's say, make both of them R, or I guess I could make both of them S? Well, how are we going to do that? Well, we know from a previous video, you just have to interconvert 2 groups, and that automatically switches your R and S designation. So let's just make this guy an R by switching that H and that fluorine right there. And then let's make its mirror image, and I'll show that, in fact, those mirror images are now going to be non-superimposable, meaning that when I switch this, I am now talking about a chiral compound, which has an enantiomer, yada, yada, yada. Okay, here is the chiral compound, right? This is not a meso compound, right? So don't be confused by the title up there. This RR, you'll notice that I just destroyed that mirror plane, so I had to erase it because now that H would reflect into that fluorine, which, is not, any kind of symmetry. And the other thing I did is I built this model right here that will hopefully match what you see on the board there, right? A fluorine going backwards and then a fluorine coming forwards right here. And I also made the mirror image, right? And so, oh geez, this is so hard to do. Here, let's just do it like this, right? And so here we've got mirror images. Take my word for it. And now we're going to try to superimpose them. Okay. There we go. We try to superimpose it like that. You'll notice that no longer does everything end up being superimposed. Therefore, these guys are both in an enantiomeric pair. This guy's chiral. That guy's chiral. One is the RR enantiomer, the other is the SS enantiomer. And of course, when you kind of look at the full picture of this thing, this and its enantiomer are said to be diastereomeric with the meso compound that we saw previously, right? And so you still have those same kind of relationships, diastereomer, right? Remember, that's kind of that trash term we talked about, where if you're stereochemically related, you're bonded to all the same different things, and your only difference is like your groups are held in kind of three-dimensional space differently, and you're not an enantiomer, right? Then you're diastereomer. Kind of confusing, a lot of strange words that we use for this thing. But if you just kind of look for those mirror planes, you're going to be able to figure out when something's a meso compound. So in the remaining part of this video, it might be really helpful to look at some three-dimensional drawings, right? And using some of the conventions we've talked about. Let's look at Fischer projections, and we'll also look at kind of realistic perspectives, and I'll try to rotate things around a little bit more so it's a little bit less easy to see, say, mirror planes and what the relationships are. So here's an example of a meso compound in a Fischer projection. And actually, Fischer projections are a lot easier to recognize certain stereochemical relationships. For instance, when it's written like this, right, I can see that there is, in fact, a mirror plane right here. So to label your asymmetric carbons, we've got one right there and one right there. Turns out that that guy, confusingly, isn't an asymmetric carbon, right? Because it's not bonded to four different things. Two of the groups that it's bonded to are the same. So these two guys, let's assign R and S. Well, this guy, let's use a different color. Let's go with blue. That guy is a 4, this guy is a 1, and now it comes down to these two. And one of the reasons I'm doing the RNS designation here is that I don't think we talked about what to do with double bonds when you're doing that Conin-Gold prelog system. It turns out what you do is you treat it just like there are two separate bonds to oxygen in terms of assigning priority. So what I mean by that is we go out here and we recognize that both are carbons, so that's the first step. And we go through in descending molecular weight order. What are you bonded to here? Well, I see an oxygen, I see a carbon, and I see a hydrogen. I do the same up here, and you'll notice that this double bond I'm going to count as 2 oxygens. And on that basis, and on that basis alone, we go through and say, well, nothing wins there. Well, an oxygen is heavier than a carbon. Therefore, this guy gets the 2, and this gets the 3. And so we do our S designation. We say 1, 2, 3. It's doing this, but keep in mind that in a Fischer projection, anything on the horizontal is pointing out at you. So 1, 2, 3 actually switches to going clockwise. So in fact, that is an R. And honestly, that's not something that was very easy for me. In fact, I'm probably screwing it up right now, and you guys will tell me, of course. But that guy is an R, and that means that if this is truly a meso compound, that must be an S. I'm going to do it without checking it because I am that confident in my ability. You go, Sean. And so hopefully this kind of helps you to see how to assign different groups priorities and also how to recognize meso compounds. Now, what would happen if I, let's say, switch the OH over here? Well, in the Fischer projection, it's really, really easy to see that I've destroyed a mirror plane. Something that may not be as easy to see if you're working with a more realistic perspective. And this is honestly one of the reasons that in carbohydrate chemistry they use Fischer projections so much. And you'll notice this is still an asymmetric carbon. And we might as well just check to make sure that everything is good, right? I'm saying that this should be an R. So there's our R. Let's make sure that this is in fact the case. So we go here, we've got a 1, we've got a 2, we've got a 3, 1, 2, 3, but in fact that H is projecting out at us, so I have to reverse the direction. So in fact that is an R. And so you'll notice that this guy is not meso, he is chiral, and not a meso compound. So let's take a look at some cyclohexanes now. Okay, so here's a nice cyclohexane. It's one that's from a previous homework assignment. You'll notice that we've got this kind of cis cyclohexane, right? The CH3 groups are both projected away from us. And you might be able to very easily see a mirror plane directly through here. And it turns out that absolutely is a meso compound. And you can certainly go through and do your RNS here, and of course it should still be the case that they're the opposite, right? If one is R, the other has to be S for there truly to be a mirror plane. But the reason that I show you this, this cyclohexane is that when you actually look at the chair conformer, you can kind of confuse yourself sometimes. So let's actually go and do 2 chair conformers, and I'll show you something that could be a little bit confusing and how to get around it. So this one isn't as difficult to see as the next example, but it's really hard when you look at a chair to really see the mirror plane, right? There is actually a mirror plane if you were to build this thing that kind of cuts through this right about there, and even here it might be a little bit easier to see. But I always really struggled with being able to look at these things and truly recognize that there was a mirror plane there. And that's where some of the skills that we picked up on in terms of taking a chair and turning it into a flat structure actually end up being really, really useful, right? Because then looking at these things, you can't necessarily see mirror planes, but up here you certainly can. But there is kind of one thing that's it's not going to be really appropriately put into this presentation on meso compounds, but it's something I wanted to talk a little bit about having to do with chair conformers. I'm just going to kind of append it on to the end here, and that's called Conformational Diastereomerism. Easy to say, huh? Okay, so this is really a trick question. It's a really involved stereochemical question, so if it's confusing, don't worry about it too much, but I wanted to make sure that you at least recognized it because it does sometimes appear on your homework. When you look at these 2 different things, right, it's really common that we're going to have questions that we have to answer, hence like why I'm saying this, because it's all over your homework for this week, where you have to look at 2 compounds and talk to me about the relationship between them, right? Are they the same compound? Are they completely different compounds? Are they constitutional isomers? Or is there some sort of special stereochemical relationship, be that being a diastereomer or enantiomers of one another? Just a really common question, right? And when you first look at these 2 different things, right, you look at them and you're like, well, how do I, how do I assign them, right? They're obviously both, they both are cyclohexanes with CH3s on them, right? But it's also very obvious that they are not, mirror images of one another, right? How could anything in equatorial position ever, be a mirror image of something with things in an axial position, right? Well, it turns out there's a little bit of a trick here. And the trick is that when you start to look at chair conformers, especially in your homework, it's a good idea to actually draw the flat form, right? And what happens when you draw the flat form of this thing, which we of course talked about in a different video lecture, you'll notice a curious thing, right? Obviously the blue and the red are on opposite sides, and they're also on carbons right next to each other. Okay, so I've taken each one of these and I've turned them into the flat version of a cyclohexane, and a kind of interesting thing pops out. You'll notice that we are actually talking about the same compound, right? And so these 2 things, they are actually the same. And we could certainly do RNS designations and we'd recognize that they're exactly the same. But there is kind of an interesting word that describes what's going on here, right? The most important is that you recognize they're actually the same. Turns out they're actually they're chair inversions of one another, right? And so we've seen this before. Well, how do you talk about this in the context of conformational chemistry? Well, it turns out what you're looking at right here, even though they are the same compound, these are called conformational diastereomers, right? And so you can actually extend this whole idea of enantiomers and diastereomers and three-dimensionality and stuff like that into like the conformational world, right? We're not going to get too much into it. This is really the only place you'll have to be able to recognize that thing. But I could do other kind of interesting things, right? I could actually take this group and project it up, right? Let's change a couple of things here. I went through and changed just the positioning of that red group right there. I made it go from axial down to equatorial up. Right? And I also made that one go to an axial up. So the good news is, right, you can still look at these two and recognize that, in fact, they are still the same compound, right? So that's the same as this, and that's the same as that. But what I've done is something really interesting with the chirality of this molecule. That molecule that we just saw, the one where this was down, that was, of course, chiral, right? It had a non-superimposable mirror image. But notice what I've done is by putting that group projected down, I've now put a mirror plane in there, which is why I included this in the meso compound section. These, or this, I guess I should say, since it's all representing the exact same thing, this is a meso compound, right? Something with asymmetric carbons that is overall still achiral. And it's really hard to look at this and to find a mirror plane. Right? To look at this thing, you'd say, well, how am I ever going to get, right, an axial group reflected into an equatorial group? And the answer is you wouldn't, right? And so what's going on when you actually cannot, let's say, rotate plane polarized light is that when this thing is going through its chair inversions, right, one chair is turning into another chair, going through that conformational diastereomerism that's really easy to say for me, what happens is that ability to rotate plane polarized light goes away because you're really kind of a time average of both of these structures, right? And so what happens is you've got this, meso achiral thing that's like rapidly interconverting, right? And overall, you're not going to be able to rotate plane polarized light. And just because I can't shut up, there's some really interesting things that happen when you lower temperature, right? Where you kind of slow down this inversion. And it turns out, if I could somehow trap through like low temperature the form here, you notice there is no mirror plane there, so you could actually start to rotate plane polarized light, right? And so it's a really kind of confusing thing. I just can't shut up. So I probably should now. I probably confused you. But just kind of recognize the utility of being able to take these chair conformations and turn them into just plain old flat structures so that you can actually make appropriate designations. All right, hope this wasn't massively confusing. We all know it was.